All right. That was a nice introduction. All right. So today we're going to be talking about real-time analytics. Uh, I want to start by asking how many of you attended the session before this one? All right. Some of you did. Because David kind of introduced big data and some of the stuff he covered. Many of you weren't in the room, so I'll recover it. How many of you work with data and how many of you are developers? Both, I guess. Yeah, my journey into data was as accidental. I was a coder, didn't really care about data, but then data happened. So this is the agenda for today. I'm going to talk a little bit about myself. Actually, I'm not going to talk about myself, but I'll give you a QR code so you can connect with me. We'll talk about analytics. We'll talk about real time. We'll talk about Pino, and then I'll take some questions and I'll help you with what next you can do. So this is me. I'm not going to go into my background. Please use the QR code to connect to my LinkedIn if you want to. There are two reasons for this. One of them is because we'll be talking about LinkedIn and how this connection works. All right, so let's start with topic number 2, which is analytics. So how many of you are in BI space? All right, so one of the things, and I wrote reports using Crystal Reports, which Venkat mentioned this morning, like many decades ago. I want to forget about it. It was not very interesting, but I was very impressed with it when I started working with it, saying, oh, this is really great. And my managers were very impressed with it, saying, wow, I know how much sales we had yesterday. Or I know the statistics of yesterday. However, I'll tell you a story. So I'm going to tell a lot of bad stories of data to illustrate the need for real-time analytics. So I was 5 years ago, I was working for Microsoft. I was in Seattle. It was cold. It was rainy. It was miserable. I was in a hotel room, and I was hungry. So I ordered using Uber Eats. And how many of you have used Uber Eats in your life? Yeah, one or two. How do you rate the Uber Eats? How do you rate it? I don't know about you, but the longer I have to wait, the hangrier I get. So I have two criteria for ordering. One is delivery time, and then the other is, of course, food I can eat. But delivery time is a huge part. And how big a tip or review how good a review I leave depends on how accurate the delivery time was. So I'm talking about Uber Eats for a reason. It uses Apache Pino. So in the beginning, data was monolithic. So in other words, okay, another story time. So I used to work for a company called First Data in 1999. And this is a credit card processing company that used to do their credit card transaction processing for 60% of the world's credit card transactions. And when they brought on a customer, so let's say Macy's is a big store in the US, when they sign a contract with Macy's, they would have to sign saying, we guarantee OLTP transaction processing times, and if our average exceeds this, then we pay you back. Because how many times have you gone to a grocery store or a gas station and try to pay by card, and it won't take the card and you just drive away and you go to the next place and do whatever? How many times? Anyone? Am I the only impatient person in this room? Maybe I am. So we had to sign this contract. So the transaction processing time is super important. But we also used to run reports against the same data. So the way we did it back then was we had a primary data, and then we had replication to a secondary data source, and all the reports ran against that other data source. right? If you ran analytics query against the production data, somebody was going to lose their job. So, because transactions were slow, we had to pay people and all this stuff. So it was a monolith. It used to be a monolith. In our case, we just made a copy of it and ran reports against it. But also the shape of the data was the same. So who knows the terms OLAP versus OLTP, right? The difference is that OLTP is a transaction processing, so it's a lot of writes. So as credit card transactions go, they get written to a database. In an OLAP, you're doing things like, give me all the sales data for Macy's today. So it's always aggregation, it's always grouping, it's always filtering. So there's a lot of other kind of transactions that happen as opposed to just, write OLTP kind of thing, which is fast writes, slow reads, OLAP, slow writes, fast read. Right? And also you want a different shape of data because you don't want the IP address of the person who's doing the registration. You're interested more in how many sales, what product sold, what was the location where this sold. So there's a lot of roll-up data, aggregated data. So that's the kind of data you want to store. So typically OLAP data schema looks very different than OLTP schema. I won't go into the details, but trust me, it looks different. I'm going to turn my phone to be mute. Sorry. Okay. Also, reports were run in batch. As I was talking about, the daily report impressed my managers in 1999. In my hotel room 5 years ago, I was pissed because the delivery was 5 minutes late. Because the screen, which is real-time dashboard, that I was looking at saying, what do you mean? You told me you were going to be here at 9:30 and it's 9:34. What's going on? So there's it's not a batch thing anymore. It's real time, right? And also in the past, people used to share the same data, as I mentioned, and now we have separated data. Okay, so now what do we have? Something needed to change. And now what do we have? We have OLTP versus OLAP. We have data that's distributed, right? So who knows about data lakes, data lake houses, right? So what's happening? We're distributing the data. Data warehouse came way before data lakes and all that stuff. And what was the concept there? Oracle introduced sharding. Remember that? Sharding? Yeah? So now what we're doing is, hey, most of the data, most of the queries in OLAP are for the last month or the last hour or the last year. Let's shard all the data from, a year ago into a different section because it's low query data. So we're segregating data in data warehouse type of things. Then we're like, okay, we're still slow. We're not running data fast enough. So we're going to create multiple computes now. So we're running parallel processing in data warehousing. So that's the next evolution of big data. And then this thing happened. Streaming data, event-driven systems, everybody's familiar with. How many of you have used Kafka? All right, so Kafka is a streaming solution invented, by the way, at LinkedIn. So remember my LinkedIn reference? Invented at LinkedIn. They open sourced it. It's Apache, and a lot of people use it now. Guess what? So is Apache Pino. Also invented at LinkedIn. Also open sourced by LinkedIn. And it's being used. And that's what I'm going to talk about. All right, so how LinkedIn solved analytics at scale. One of the first problems that LinkedIn had was if some of you actually scanned that QR code that I showed, what's going to happen is that you're going to go to my profile page, and if I go on my phone and bring up who viewed my profile, which is this right here, I will see that. So as many of you, it's immediate. There's a Kafka message that happened as soon as you clicked on my QR code that goes, and then it gets consumed by who viewed my profile page, and it's shown. So that's a real-time dashboard. So that's a complicated problem. How do you solve something like that? You're like, oh, people around the world have looked at your profile, Barkha. How do you keep count of that from a Kafka message? Some of you might say, oh, that's easy. You just create a counter. Every time your profile is hit, the Barkha count goes up, right? Who viewed my profile? But it's a little more complicated than that, because you also have things like, if it's my friend, then it'll say, John Doe saw your profile. If it's somebody that's not my friend, and that has a security level set to only my friends, my first connections can see my name, then it'll say things like, somebody with the title software engineer saw your profile, or 10 people with, right? There's also another layer of logic that people don't realize. It actually detects your title and shows the higher title first. Anybody notice that on who view your profile? So you'll see somebody with the title CTO saw your profile, then there's like 3 people with the title a recruiter saw your profile, and then 5 developers or whatever. So it's a little more complicated than just a counter. And how many counters are you going to create, right? 700 million plus people times how many titles? That's a lot of counters. So before Pino, so they invented Pino, by the way. They were not trying to invent a OLAP database, a real-time OLAP database. They were trying to improve performance. And before Apache Pino, they were using Elasticsearch-based solution. So each one of those messages was a document in a store somewhere. Elasticsearch indexed it, and they were running 1,000 nodes. At the time, they were serving 1,500 queries per second, and for 20 plus million users at the time, 700 plus right now. So what they did was they started iterating on the source code for Elastic. It used to be open source, not anymore. But they started iterating, and they started creating optimizations on it. And they ended up with a product called Apache Pino. They applied for the Apache license. They released it. After Pino, they went from running 1,000 nodes, parallel computes, to 75. And they were, remember, they were serving 1,500 queries per second. They went to 5,000 queries per second. And by this time, there were 70 plus million users, so more than doubled, more than tripled. So a lot more data, a lot more efficient, and successful. So you should be asking how, right? All right, let's talk about how. All right, so before we go into that, I just want to define what it is. Apache Pino is a real-time distributed OLAP data store designed to answer OLAP queries with low latency. The 3 things that the engineers who created this were looking to solve for was, of course, latency. So the amount of time it takes to execute a query, that's latency, how quickly you can get results. Concurrency, because 70 plus million users, granted, not all of them are looking at who viewed my profile at the same time, but still, it's a large number. So 5,000 queries per second is what they were serving. Last we checked, that's concurrently, right? And freshness. So who viewed my profile 2 years ago is not interesting to me. Who viewed my profile today is interesting to me, right? So the value of the data, depending on what kind of data it is, but typically on a user-facing dashboard, such as LinkedIn, who viewed my profile, is valuable, or Uber Eats order delivery status, is the fresher it is, the more usable it is. the stale it is. I'm not interested in my food delivery status 1 hour after delivery. I am very interested in it 1 minute before delivery, right? So the fresher it is, the more useful the data is. Okay, so let's look at the architecture a little bit. I'm going to talk a little bit about this from, again, more horror stories from my past. So I talked about first data. If you notice, this is the architecture. So there's a controller, which comprises of, again, Apache Zookeeper, Apache Helix. Apache Helix is cluster management software. Zookeeper is a state management software. Again, Apache products, open source. Kafka also uses Zookeeper, by the way, for state management. And then we have the broker, and then we have two flavors of servers, real-time and offline servers. We have segment, and we'll go into it in a little more detail. There is an ingestion job and raw data. So why real-time and offline servers? So going back to 1999, working for First Data, in July, we would sign contracts with people saying, hey, I know Christmas is coming. We need you to sign contract now if you're going to issue new credit cards. Because guess what? On that database, the OLTP database, we had to load millions of credit cards. And we couldn't just ingest it because the server would go down, because we had all those contracts saying we owe you money if the transaction processing went down. So we would find quiet times and run 100,000 ingest at a time every night for months to accommodate the hundreds of customers that we had with millions of credit cards that needed to be issued. So that's how we were doing it, because we didn't have a strategy of this separation. So in Apache Pino, it's separate by design. So you can ingest using offline servers, has absolutely no impact on your real-time Kafka processing. And it supports other than Kafka. It was originally created to deal with Kafka because they were not looking to create a product. They were solving their own problem, right? All right. One of the things I want to talk about is one of the ways they improved the OLAP query times is by going columnar. So why columnar? So think about a typical OLAP query, which is like, hey, give me the total sales, which is the aggregation, for product or location X, and group by hour or day or something for this week, right? So now we have aggregation on top, but then before that aggregation, there's some filtering saying, hey, give me for only this location, for only last week. So when you're doing that kind of stuff, reading the entire row in memory is costly. But if you just go against the columns and say, oh, just give me these are the records I'm interested in, it's more efficient. You don't have to load rows, in memory, so indexes are more efficient. And so that's why columnar works much better than row. So that's one improvement. We talked a little bit about separation of batch data and streaming data, segregating it from ground up. What happens is if you have a situation like First Data, where you need to load 1 million credit cards, no big deal. It'll get done through that guy, and the streaming ingestion is going on, and no difference, no problem, no impact. A little bit about how it's the structure of Apache Pino is. So you have clusters. You have a cluster. A cluster has a lot of different flavors of things, such as brokers and controllers and Zookeeper and Helix and all that stuff. And it also has online, offline servers. It has something called Minion, which is more a task runner. So it's an on-demand kind of thing. Then you have this concept of tenant, which is it's not a physical thing. It's an abstraction to segregate data between two departments, say, or whatever, for security reasons. Then you have a table, which is also a concept, and it comes in 3 flavors. So it can be online, which is a streaming data, offline, which is a batch data, or it could be hybrid, or it could be both. And then we have segments. So instead of those shards, tables are comprised of segments. So segments are the building blocks of data, and how is it stored. So this is what a segment looks like. So you have, let's say, server 1, server 2, server 3, server 4, and the colored little dotted boxes are the segments. And so you'll see that segment helps in 2 ways. Each server is responsible for 1 or more segments, and each segment is actually replicated across servers for 2 reasons. One is if a server goes down, no worries, we still have the data somewhere else. We can re-up the server in our own time. And the second thing is, if there's a lot of queries against this segment 1, the broker can actually send some queries here and others here. So it's also good for load balancing, right? So Pino Broker, you've guessed, is doing the where do I send my queries work. So it's doing scatter gather, kind of similar to MapReduce, but not. And I wrote an article on it, so I'll link the details of it. Just know that it's similar in concept to MapReduce, but it's different because it can, in a scatter gather scenario, you can apply iterative functions to it. So you can do roll-ups and scatter gather and things like that because it's an OLAP store, right? It's not a search solution, it's an aggregation solution. Slightly different needs there. It also has tons of indexes. So a lot of indexes were created for Apache Pino. And so when I said, they didn't set out to create a product, they were just iterating and improving on what they had. These are some of the steps. So the inverted index, so forward index is a typical text index. I don't have it here because it's default. Most text indexes, including Elastic, uses forward index. So forward index is, you have a document, and in the document, you know all the words that are in that document. You can find anything in that word. An inverted index is that you have a word, and you know all the documents where that word belongs. So you know where to go to get that word. A range index, slight improvement, because if you think about the first use case, LinkedIn use case, it's, hey, who saw my profile in the last week? Time series data, right? It's all based on time. So instead of saying, hey, today somebody saw this, yesterday somebody saw this, it says for these 5 days, the data is in this document. So it's a range rather than inverted, one pointer per record. Text index, it has some enhancements that they made internally for text index. Geospatial, guess why we have geospatial indexes? The clue is in one of my stories. Because Uber. So Apache Pino, Mountain View company, Silicon Valley company, LinkedIn, some people left and went to work for Uber saying, hey, this problem was solved at LinkedIn, let's use it. And they said, hey, can you add a geospatial index? And it's based on H3 standards. This is a 1-hour talk on its own, but it basically gives you a fast way of finding the distance between 2 points using hexagons. JSON index, because we're dealing with messages, right? So if there is a JSON message, it allows you to customize things like how deep do you want to parse, how deep do you want to index. You don't want to index everything by default. And then star tree index. This is the reason the company's name is Star Tree, because they invented this index called Star Tree. So how many of you have heard of cubes? Do you know what cubes are? Yeah, so cubes are basically pre-aggregated data. So, the example of what we were talking about, hey, what was the sale, daily sales, right? So you could just aggregate it, daily sales. The next iteration, of course, is, somebody sees that, oh, we have daily sales and it's really fast. Can I have it by country? Can I have it by location? Can I have it by product? Can I have it by department? And now what happens is that the cube kind of grows exponentially. You have tons of storage. Some of those cubes don't even make sense because the aggregated result would be 1 or 0 or something like that. So you end up creating all these cubes that become complicated to maintain, slow to write, and not very efficient. So Startree, the team, invented this thing. What is this thing? So here's a simple example. This is a very simple example. It's not even worth using it, but it's extremely efficient in high-dimensional data, right? So let's take an example of browsing history of a website. So we want to track where the people came from, which country, and what browser they used, right? Those are the two cubes we're interested in. So in a star tree index, what happens is that you have a root node, and then what we do is, okay, 80% of our traffic is coming from either US or Canada. And then, give or take 200 other countries. Instead of creating a cube per country, they create a cube for US, Canada, and then everything else goes in a star. Now, two things happen. One, you're not creating a cube for, and I'm not picking on Kiribati, but for Kiribati. Maybe there's 0 people who browsed from Kiribati, right? So you're not creating a cube per country that doesn't have any data. And then the second thing is, once you remove the 80% of the data out of that, this is such a small bucket that you can use normal indexing principles to roll it up, and it's not a big deal. So even if you were to say, well, how many from Lithuania? That's fine. It's a small enough data set. We're not dealing with 100% of the data set now, right? So that's the first level. And then for each one of these, there's also a cube of what browser. So let's say that Chrome and IE are Edge, whatever, are 80% of the data. Again, what we'll do is we'll create pre-aggregation cubes for the 2 that are interesting, and then everything else goes in the star. And again, the same principle applies on this. So every node has one of these. And so what ends up happening is, for the data that's most used, the path to finding the rows or aggregation is 2 steps or 3 steps. It's still very fast because it's pre-aggregated, and the stuff that's not that queried it's not pre-aggregated. So, but it's fast anyway. So I will tell you that the customer support team, once they roll out Apache Pino for a customer, after about a month or so, they come and they say, well, we'd like to improve the performance. And all they do is create a star tree index, and then boom. There are people who are like, I think there's a bug here. Something's wrong because it's too fast. So, true story. Will not tell you what. All right, let's do a demo. Don't believe anything that I say. Let me prove it to you. Okay, so let me see if I can do this. Let's extend. Actually, let's duplicate. All right. Keep changes, and let's take a look at. So this is a public GitHub repo, and you guys are all you should be able to. So this is where it is. It's a public repo. I just have it locally. And what I'm going to do is I'm going to Actually, let me bring up my Docker desktop. So this is Docker desktop. I have the images because the images take a long time to download. But what I'm going to do is just kill the container to prove to you that, you know, all the containers are gone. Images are here. It takes a long time on this internet to download the images, so I'm not going to do that. But let's go ahead and run this. So this is just a Docker compose and command, and it's in the documentation. I'll walk you through the documentation too. So while this is running, let me go to this and tell you what's going to happen. So we are going to emulate running a pizza shop demo. And so typically what will happen is there are orders being come in through, you know, whatever, web, phone, and then they end up in a Kafka queue. We have a MySQL server that has the product details, and the only reason we're using the product details is because we created a pretty dashboard, and so we need product images in the pretty dashboard. So totally not needed, but whatever. So what happens is that the order service, so we wrote an order service that's emulating orders coming in. So it's just creating orders randomly based on the products, all hard-coded products. And so it ends up in a Kafka queue. Then from the Kafka queue, Pino takes it, enhances it, including some product images, so we have a pretty dashboard. And then we have a Streamlit dashboard that shows what's going on. All right, so let's check on our dashboard and see what's going on. Let's go here. Let's go to containers. What's going on? Oh, things are running. But this guy is not running, and this has a bug in it, and I purposely did this so I can show you some of the stuff. So here's what the Pino dashboard by default looks like. So I have my edge here, and this is the Pino dashboard. It's by default 9,000, so this is what it looks like. You can see that it has one controller, one broker, one server, 0 minions, one tenant, 0 tables. Okay? So here's a zookeeper. You can see these are Kafka brokers, and you can already see some stuff in here. But what we're going to do is we're going to go to Swagger and create some tables. Slowly but surely. It's coming. All right. So the way you would do it is you would create, and it's all JSON. So we'll create a schema, and then we'll create the tables. So let's do schema, try it out, and go back to my, so let's select all. I'm just copying and pasting it in my dashboard. So this is my schema. Execute. And it says 200. Wonderful. Let's create a table. Select all, cut, and go back to here. And where is my tables? Uh-oh, lost tables. All right, I'm just going to go up here, and demos are fun. Definitely not broker. There you go. All right, let's do, where are you? Add table. Okay. And I'm going to create this table. Execute. And just to prove to you that I'm not just making this up, let's refresh this. And voila, there's a table. All right. This is, let's run some queries on this. And it has some stuff. Run queries, and you'll see that the number is going up. Total docs is going up, right? Because that the service, the order service is just generating. For the dashboard to work, we also need the orders enriched schema and table. So let's do that. Select all. Sorry, I talk when I code, so I apologize. Go back to Swagger and find schema. Here. So we'll create this, execute, and it says 200. Good. Now let's create the table again. Go back here. Go up to the table creation and see if we can create this table. Execute. Okay. So now we should be able to see two tables. Voila. Let's go to the Streamlit dashboard and see if it's working. All right, so we need a third table, which is orders. So let's do this. Select all. Go back to this. Swagger, go to schema. The schema is below table for some reason. I know this is a little boring, but bear with me, it's worth it. Select all, copy. I wanted to make sure that I'm not just showing you screenshots, and I'm actually showing you real stuff. And so this should be the table. Execute. We'll go back to Apache Pino and see if there's a third table. Yep, third table. Let's see what Streamlit is doing now. Oh, look at this. There's some stuff here now. 989 orders in the last second. Average order 4,005. I'm making a lot of money here. And then this is the real-time order screen. And it should update. I think it's updating every second. But, oh, 1 minute. Yeah, okay. Every minute. So the last, it went down. We just have 970 orders in the last second. But you'll see that the beautiful images keep updating, and there you go. Voila. Real-time dashboard, ladies and gentlemen. Okay. I'm going to stop this order service, otherwise I will run out of memory to, to finish my demo, my presentation. But what do you think? Impressive, right? So what happened? We were able to stand up a Docker Compose with Kafka consuming messages, Pino consuming messages from Kafka, and Streamlit querying Pino and getting results very quickly. The LinkedIn feed, so more than 100 dashboards exist on LinkedIn now. So pretty much if you're using LinkedIn, you're using Pino. Also, if you're using Uber, you're using Pino. If you're using Stripe, you're using Pino, and so on and so forth. So this is another, here's the actual query that they run. And here are some numbers on it. 700 plus million now, and the latency is less than 100 millisecond. Queries per second, more than 100,000. Total users, 700 million. Uber Eats, this is the restaurant manager I was talking about. And you saw a small demo of the pizza thing we created, kind of based on it, but not really. Just a very toy problem. Running on my Surface laptop, so come on. And here's some of the people who use the product. And this is an older slide, so there's more now. So, questions?